Let's now take a look at how to do collaborative filtering using matrix factorization. So in the matrix factorization approach, we aim to characterize the items and users using vectors of factors learned from the rating matrix. In this way, a high correlation between the item factor and the user factor will indicate a good recommendation. And this will have the flexibility for us to incorporate implicit feedback, temporal effects, and confidence intervals. So the basic matrix factorization operates like this. So we will map the users and items to a joint latent factor space of common dimensionality K. So item I will be associated with a vector Qi. And this Qi is K-dimensional, and it indicates the extent to which the item possesses those K factors. Yes, in the space there's K factors. And user U will have a vector Pu to indicate the extent of interest the user has on those K factors. And then we can model the user item interactions to find out the user's overall interest in the item's characteristics. And this can be done by an inner product between Qi and Pu. And this will give the predicted user use rating on item I. So that will be our prediction. But how to learn this matrix factorization model? What we want to learn are the item factors Qi and user factors Pu. Let us look at how to do factorization when we have a full rating matrix with no missing entries. If our matrix R has no missing entries, we can factorize R using singular value decomposition, or SVD, to obtain three matrices, P, S, and Q. Okay, so that is called singular value decomposition. And here is a typical illustration where A is our R over here, the rating matrix, and U is our P over here, which is user factors, and V is our Q over here, which is the item factors, right? Which are contains the item factors. And sigma over here is our S over here. And this R over here is our K in our problem. It's a K in our problem. So the next step is to reduce the matrix S, as the matrix S, to a dimension K, so dimension K. That is R over here. I just reduce the dimension. So SK will be K by K. So then we reduce P to PK and Q to QK, which is a pink area over here. That's a pink means a reduction. And then we can form two matrices, P hat and Q hat, right? So then once we have this, right, so this is P hat, right, so this is P hat and Q hat, right? So then the use row of P hat, that means each row here will be a factor for the user, right? So each row corresponding to a user, and then each row will give you the user factor. And over here, each column will give you the item factor. However, we have assumed that the rating matrix has no missing entries, right? But that is not the case for recommender system. If there's no missing entries, then we have all the ratings we don't need to do recommendation, right? So the reason we want to do recommendation, want to learn a model, is because most of the values are missing, right? Most of the values are missing. A high portion of missing values, right, so is caused by the sparseness of the rating matrix. And in this case, the conventional SVD is undefined, right, because the knowledge of the matrix is incomplete, right? So we cannot perform SVD in the regular way, right, in the conventional way. One solution is to fill in the missing values, right? So in a common imputation approach, we fill in the missing ratings using the average ratings for the users and items. But this approach has two problems. First of all, it will make the process very expensive because it will increase the amount of data significantly. Because the matrix is sparse, if you fill in all the entries, it will significantly increase the amount of data. For example, if originally there's only 1% of the entries, right, so has values and 99% are missing. If you fill in those 99% missing entries, the data size will increase by 100, right, almost by 100 times. Secondly, by filling in the average rating, right, the average rating for user and item, it is inaccurate, right? So it is inaccurate because you cannot just assume that the user will give an average rating for that item, right? So this will distort the data, right? Because once you fill in, they will be considered as real, right? So it will distort the data. So the solution is let us model only the observed ratings, right? So we observe using the observed ratings directly in modeling. And we will also avoid the overfitting using a regularized model. And this gives us the objective function like this. The objective is to minimize the regularized squared error on the set of known ratings to learn the factor vectors P and Q. Right? So P and Q are what we want to learn. Right? P and Q are what we want to learn. And we learn this on the set of U and I from the training set, right? The training set is called K, kappa over here, right? The training set. The training set has known ratings, right? So therefore, ratings for U and I in this set are known, right? Are the training data. They are the training data. And this is our estimation Q and P, right? So therefore, this is a prediction, right? So therefore, this is a prediction error, squared prediction error. Second term lambda is a regularization parameter, and this is to prevent overfitting, right? So by regularize what we want to estimate, right? QI and PU, right? So we regularize. So there's a penalization on the size of the norm of P and Q. Now let us look at how to solve this problem, right? How to obtain the optimal Q and P. From this objective function, we see that we have two sets of unknowns, right? Both P and Q, they are unknown. They are unknown. The solution is called alternating least squares, right? So in this approach, we can fix one of them, one set, and then we will have a quadratic problem with an optimal solution. So this is called the alternating least square approach, or ALS. Right? So the solution is to alternate between fixing Q and solving for P, and fixing P and solving for Q. Right? So therefore, for example, we can start with fixing P, right? Fixing the user factor, fixing the user factors as P hat, and let's recompute, right, the item factors. And we recompute it by solve solving a least square problem like this. Right? So therefore, the optimal solution is the rating matrix PR will equal to P hat times QT, right? Q transpose. And by solving this, we can obtain QT equal to this, right? So then we update, right? So after this, we can update our item factors. And then next, we can fix the item factors as we obtained from here, as we fix it as here, as Q hat. And we can obtain P like this. And of course, in this alternating approach, right? So we have to start with something, right? So therefore, you need random initialization to start this iteration. And so if you start with P, you need to randomly initialize the user factors. If you want to start with Q, that's fine, right? So you can, but you need to randomly initialize the factors for the items. So this is a very nice illustration of this ALS approach for matrix factorization for movie recommendation. And so here the ratings are obtained from the users for a set of movies, right? So the rating matrix user by movie. And in this factorization, we learn the user factors, right? So each row of the user matrix, right? User matrix factors, user factors, and this is more like Q, right? So QT, the movie factor. Each column is a movie factor, right? So we write it both as Fi or Fj, right? They use the same notation so that you can write it as a single function, right? So here are the user factors, F1, F2, right? So as the example, and here are the movie factors, right? So these are the movie factors. So their relationships are the ratings, right? So this, if you know about graph, right? This is actually a bipartite graph, right? So this is a user factor with a movie factor, right? So their interactions are the ratings, right? So if you do a inner product between the two, you get a rating, right? So that is so they write the objective function as this, right? So in a more generic form. So this is one of the factors. For example, if we are solving one of the factors, right, this is assume that the other factors are known, right? For example, here assume the the factors, one of the factors is known, and we solve for the other, right? So therefore, this is the neighbors, right? Neighbors of I means those with ratings, right? With ratings. I is the user, so this J means those items that rated by user I, right? So that is a different way of writing the objective function, right? So in just one of the term, right? In just one of the terms. And here they are optimizing W, right? Here is optimizing W, right? So the solution of W will give you the user factor, right? So Fj here is a movie factor. So here we are trying to assume that Fj is given, right? So we fix Fj, movie factors, and looking for the user factors, right? So that is matrix factorization for collaborative filtering, right? We take an alternating least square approach to solve the problem of factorization with missing entries. In the last section, we will look at how to do scalable collaborative filtering in Spark.